Some of you may have seen a video at one point earlier today where I had something like this, and I went over the demonstrate understanding that my first block is already done. My third and fourth did not get a chance to go over that today. So I removed that off of YouTube, and I am posting this now where I work through some of the practice problems to help support those of you who need some extra before your demonstrate your understanding. And so I'm going to turn off the camera right now because you don't need to see me while I work through these problems. I'm going to come back to numbers 1 through 3 like I did previously in class. I'm going to start with some of these problems down here. Okay. We talked about it in class. The very first thing you need to always do if you're going to try to write an equation is using the type of representation, identify the type of relation as linear or exponential, because then you can write out your equation. For instance, when I'm looking at number 5 and I'm looking at a table, I instantly am asking myself about rate of change. Tables reveal rate of change. I could also graph these points and it would show me a very similar story. But what I notice is +2 +3, because I always move left to right. So from my negatives to my positives in the x, I'm not constantly adding by the same thing. My immediate next thought is, well, if I'm not constantly adding by the same thing, am I constantly multiplying? And so I use my F for constant factor, for that constant multiplicative rate of change to represent and figure out, do I have a constant multiplicative rate of change? And so what I'm seeing now is 4 times F is equal to 6. I can solve this equation by dividing by 4 because 4 divided by 4, or a fourth of 4, is 1. Whatever I do to one side of the equation, I have to do to the other. And that gives me a 3/2. And if I check, 4 times 3/2 is 6. 6 times 3/2 is in fact 9. And 9 times 3/2 is 27/2. And somebody may be asking, well, how in the world did you know that, Mr. Kinney? You moved too quick. Well, here's how I know. 4 divided by 2 is 2. And 2 times 3 is that 6. 6 divided by 2 is 3, and 3 times 3 is 9. And so this is why I like to use fractions and why I don't say 3/2, but I understand that fraction bar means division because it helps me see the next piece clearly. 9 times 3 is 27 divided by 2. It's all right there in the story. And I can see this as well if I were to make a graph. I'm going to scale the y-axis by 2s because I don't have a ton of space. And so I've got the point -3, 4. I've got the point -2, 6. I've got the point -1, 9. And I've got the point 0, 27 divided by 2, which is 13.5. And I know this is that exponential function. And so my equation will be, oh, and I should have written this originally. As soon as I realized it was exponential because of that constant factor, there's the pieces to the equation with my y-intercept and b being my constant factor. Remember that variable exponent literally is showing repeated multiplication. And so I can see my y-intercept here. Remember the input is 0. So there's my y-intercept times my constant factor, which is 3/2 raised to the x because I'm repeatedly multiplying by 3/2. You can do a very similar thing with number 6. I see a table, but I want to recognize in this table that I am subtracting by 6 in the y and adding by 3 in the x. But on both sides, it's a constant additive rate of change, so I know I'm dealing with a linear function, or y equals mx plus b. And don't forget, quite literally, what is happening between the m and the x is they're being multiplied, because multiplication is a constant, repeated addition. And also, that constant additive rate of change is literally called slope. And we calculate that as the change in y divided by the change in x. The change in y is my -6. My change in x is 3. When I do -6 divided by 3, I get -2. And then when I look at my b value right here, right, you've always got a rate of change and a y-intercept, slope, intercept. That is true for both linear and exponential, at least for these two forms, the only ones I'm asking you to use this year. And so don't forget, you can make a graph to find your y-intercept, but every y-intercept that has ever existed and will ever exist has an input of 0. That is because on the y-axis, so I'm transitioning back over to the exponential function earlier, notice I have -1 and 1 in the x, and right in between that is my y-axis. And the x value between -1 and 1 is 0. Every y-intercept that has ever existed has an input of 0, which I don't see on this table for the linear in number 6, but I can find it because I can keep going backwards by 3 in the x values. And then I'm going to go add 6 to the y values to keep going correspondingly. And there's my y-intercept of 38. M was -2. 38 was B. Now, things can get a little bit trickier when we move into a graph, but they definitely don't have to be. The only difference with a graph versus a table is that a graph, it's harder to see the rate of change. And a lot of students, when I'm looking at number 7, they're going to want to do rise divided by run, +4 to the right 1. But the issue is remember, slope is a constant additive rate of change, so that's not going to work here. So I'm not doing that. On top of the fact, if I were to check the rise here divided by the run here, that would be plus, I think, 12. Notice that's different. It's changing. It's not constant additive. But if I look at a simple table, and I can't clearly tell that point, so I'm not going to use it, but I can clearly tell this one on the y-axis is 0, 2. I can clearly tell this one right here has an x value of 1 and a y value of 6 because I count up 6. And the final one up here is 218. Now I can easily tell that I'm multiplying by 3. I don't even have to do the fancy times f to figure out what the factor is. I can clearly see that I'm repeatedly multiplying by 3. And I didn't even have to make the table to know this is exponential. That's literally an exponential curve. So as soon as I see that graph, I know I'm using this equation because it's an exponential curve. And I know A is my y-intercept, B, the thing with the variable exponent, because exponents show repeated multiplication, that's my constant factor. I can see my y-intercept of 2 times my constant factor of 3 raised to the x. And that's how I write the equation. With number 8, it's a little bit tougher for some, because I don't see clear points here or here or here or here. And we're used to having a ton of points for my graph or for my table, but these are the only 2 in blue that I actually see. But that's enough. Because as soon as I look at this graph, I know it's not linear. Knowing it's not linear, I can actually start to see that exponential equation or exponential curve right there. So I know it's an exponential function, and I'm going to use the equation for an exponential, where A is my y-intercept, and I already have that. That's 80. All I need to find is my constant factor, and I know for a constant factor, 100 times f is equal to 80. And I know how to solve an equation like that. The inverse of multiplication is division. And when I type 80 times 100 into the calculator, it gives me a nice factor of 4/5. So my y-intercept is 80 times my constant factor is 4/5. There is the equation for that function. And so you can do the same thing with number 9. I've already given that solution in the answer key that I gave you. Number 10, I just want to point out, I don't have a table, but I could easily make a table just by identifying the points. And you don't have to. And in fact, I probably wouldn't. The only time I would definitely create a table is when I'm trying to convert with exponential. I can clearly see, hey, that's a line, so I know I'm dealing with the equation f of x equals mx plus b. And I know m, my constant additive rate of change, my slope, is the change in y divided by the change in x. Pick any 2 points. It'll give you the same exact slope. So change in y was -3. Change in x was a +5. And if I went from this point in the bottom right up to the y-intercept, it's going to give me exactly the same story. It may look different, but I'm going up 6, and I'm going to the left 10. And if I take 6 and I divide it by -10, I still get -3/5. And I see my y-intercept as 0, 2 on the graph. So my equation just comes out to be -3/5 x plus 2. Last couple of things I want to point out is when I look at number 11, there's definitely nothing I can multiply by 6 to get 2 then 0. And if I look at what's happening in those y's, it's definitely not constant additive. So this is neither linear nor exponential. But what we have started to look at just today even, actually really last Friday with Dr. Johnson, is that this is constant additive. And we know that a linear function has a constant additive rate of change. Well, this then is a linear, not function. We're adding with it. This is a linear additive rate of change, which that is what defines a quadratic function. If you were to graph those points, you would see a parabola. Connecting that here, I just want to point out that I have traditionally put questions just like numbers 1 through 3 on assessments in the past. And I'm telling you this equation is correct. I'm just asking you to explain why. Well, when I look at number 1, I see an exponential curve, so I know it's an exponential function. And I know that a is my y-intercept. And hey, there's a y-intercept of 6. That explains this 6. I know that 1/3 is my constant factor, so I need to find that constant factor. And if you make a quick little table, there's the point -118, 0, 6, and 1, 2. It's like you're multiplying by 1/3 every time for a constant factor of 1/3. That's it. That's where the constant factor is coming from and where the y-intercept is coming from. Looking right here at number 2, you may despair and say, but Mr. Kinney, I don't see a 3/4. That's okay. As I'm looking at this, I don't see a 3/4 either, but I know that that's the equation of a line. I've got multiplication between 3/4 and x. That multiplication indicating constant additive rates of change. Wait, that constant additive rate of change is called a slope. If I take -6 divided by, sorry, that should have been -8 here. -6 divided by -8 is simply a 3/4. Boop. There's my slope. And then I still need a y-intercept, right? We always need slope and or rate of change in y-intercepts for these linear and exponentials. And so if I keep this pattern going, that input of 0 has an output of -12. There's my y-intercept. That's it. And when we're talking about these graphs down at the bottom, if we're trying to graph or create a table, there's 2 things to always remember. One, if you can identify your y-intercept and identify your rate of change, you're going to be solid, like in number 6. I know that this multiplication is constant additive rate of change, so that's my slope. Even though it's backwards from mx plus b, it's still true. I can switch the order as much as I want. My y-intercept, 0, -4. The input for y-intercept is always 0. And then I have a slope of -2/3, right? Change in y divided by change in x. And so I'm subtracting 2 from the y. And as I subtract 2 from the y, I'm going to add 3 to the x. And I just got to reverse that if I'm going backwards. And there's a table using my slope and my y-intercept. Same thing if I'm trying to graph it. 1, 2, 3, 4, -4. Slope of down 2 to the right 3. And I've run out of room this way, but I can go the other way. If you check these points, those points line up or map completely to the table, because the graph, the function or the equation, and the table are all equivalent, the same inputs mapping to the same outputs. What I would also point out is if I were to look at m of 0, remember you can, or h of 0, you can always substitute inputs in and get outputs out. 0 has taken the place of that x, so I'm substituting 0 in for x. And if you simplify this expression, I get -4. 0 is mapping to -4. Now you'll notice I went by threes because literally, if I understand this equation, I'm dividing by 3. That's why I did the next x value is 3 in the table. And so when I do that, substitute 3 in for x. 3 divided by 3 is 1. -4 minus 2 is, you got it, -6. 3 is mapping to -6. It doesn't matter how it's looking. You can do the same exact thing with number 5. We did number 5 in class today, but we just need to recognize, hey, this has a variable exponent. So this is exponential, and exponential typically is a times b to the x. But again, I can switch that order. 2 times 1/3 to the x. It's that variable exponents that's defining my constant factor, what I'm repeatedly multiplying by. And so I can see a y-intercept of 2 as a graph or as a table. And I can see that constant factor of 1/3. And so 1 would be 2/3. 2 would have mapped to 2/9, constantly multiplying by 1/3. And if I want to go backwards, instead of multiplying by 1/3, I'm going to multiply by 3, multiply by the reciprocal. And if you are like, man, I don't like having to use that constant factor, using that rate of change, that's totally fine. It's a little tough for some students. You can always substitute inputs in and use a calculator if you need to. The negative exponent indicates to divide or multiply by the reciprocal. And that's just 6. The input of -1 maps to 6. The input of 0. We talked heavily today in class, how about anything to the 0 power? We talked about y, but it is equal to 1. So 2 times 1 is 2. 0 maps to 2. I don't care how you get there, but whether you use the y-intercept and the constant factor, or whether you just simply use inputs and outputs, it's your choice. But we've got to learn how to find those graphs and those tables, because different representations reveal different parts of the function and make different things easier. So that is more time than I meant, but hopefully that helps some of you understand how to create tables and graphs for linear and exponential and write the equations for linear and exponential.